So if you remember, I gave you an aim to determine the projected range of a ball bearing rolled down a ramp. We might change that to test the effects of the exit velocity on the range of a projectile. Why is this important? Well, knowing what variable you're looking at will actually determine what formula you want to use, and also then what you're going to rearrange the formula into to calculate for the variable that you're interested in. So let's go and have a look at deriving the formula. And first thing that we need to do is let's just, I guess, look at the experiment that we're doing as an overview. What are we doing? Well, we're going to get a ball bearing that leaves the pipe, and it's going to go and it's going to fall. That's not a very good parabola, but that should be a parabola. And what things might we be interested in? Well, we might be interested in the time of the flight. That might be interesting to find out. We might be interested in the total displacement that the ball has, so x. So let's call that x at the moment, or it could be what we might also call it is range, or r. We might be interested if we're in one of those big tall ships and we're shooting cannons and ball bearings. If we're shooting cannonballs and we're trying to hit another ship, well, we might want to know at what angle do I shoot that the cannonball at, so that it hits and sinks someone else's tall ship. That might be interesting. The range might be really interesting. So how do we go about then, I guess, sorting all this stuff out, all these formulas, and how do we then rearrange a formula to get what we want? Well, we can start off with another, I guess, if we look at this ball bearing again, this time of flight. Well, there's something that we can assume in here, that what we know is this total time of flight, TF, is 2 times the time it takes for the ball bearing to drop from here to here. So if we were to get a ball bearing and drop it from this point here, and it hits the ground, that would be the same amount of time that it takes a ball bearing to go from this point to here, or the same amount of time it takes to go from this point down to here. So that's interesting, because we have a whole lot of formulas on this, and these are the sort of one-dimension formulas that we've been using. So we've got a couple of things. We know this. We know that if we drop a ball, that V equals U plus AT. And because we're now doing 2 dimensions, we can call this Vy or Vx. So because we're dropping it downwards, we're going to call that Vy. So we know that Vy equals Uy plus AT. And we also know that A is actually G. So we're going to say Vy equals Uy plus GT. Now we also know something else that's in here with this Uy component. And we know that if we shoot an object, or if we put a force on an object at a particular angle of theta, that we can go and get this resultant vector here. So let's say that's UR. So I'm going to call that UR, which is the resultant velocity. That velocity there is equivalent to, or can be broken up into, 2 components. It can be broken up into the UY component, and it can be broken up into the UX component. And if we were going to calculate UY, let me change colors here, and let's go and do some work in a different color for a second. We know that this is the opposite side, and we know that this is the hypotenuse, and we know that this is the adjacent side. And to calculate the opposite side in a triangle, we know that sine of theta is equal to the opposite over the hypotenuse. So if I want to calculate the value for the opposite side, I multiply both sides by h, which cancels that out, and I multiply that by h. So I end up with h times the sine of theta is equal to the opposite. Now if we go and reallocate some of these variables to what we've got in this triangle up here, h, the hypotenuse, is UR. So if I go and get UR times the sine of theta, the sine of my angle, that is going to be equal to Uy. So up here where I've got Uy, I can now go and substitute in and say that Vy, let's get my pen again, that Vy is equal to UR sine of theta plus GT. So let's go and draw a little box around that because that's a pretty important formula to start with. The velocity in the y direction, that's this velocity here, that initial velocity in the y direction is equal to the initial velocity in that direction that it shot out of the cannon at, multiplied by the sine of theta plus gravity times time. Now we said, I mean, we could, I guess, be happy with calculating the velocity, but we said before that one of the things we might want to know is the time. This time here, we might want to know the time. So what about if we now go and rearrange for time? So we want to have the time is equal to something. Well, what we're going to do is we're going to take the time, the rearranges formula so that we end up with u r, I'm just going to call that u, sine of theta, u sine of theta minus vy all over g. Okay, and I can do something else with this because if we're calculating the time is not the time of flight, the time is this time here to drop from there to there, or the time taken to go from here to here. It's only half the flight. And if that's the case, like we do when we did our formulas for one dimension, our linear motion formulas in one dimension, in this case here, Vy, the initial velocity, we can assume to be 0, which means that my formula now becomes the time of flight, or half the time of flight, the time that it takes to fall, or the time it takes to reach the top of the flight, or from the top of the flight to the bottom, is equal to u sine theta over g. Okay, and so what can we do with that? Well, we still can't do exactly what we want, but we're getting closer. If that is the time it takes for it to get from the top to the bottom, or from the bottom to the top, well, we actually want twice that, don't we? We actually want to have that times 2, which means we need to multiply this by 2 as well. And instead of being t times 2, we're going to call that a new one, a new letter, a new variable. We're going to call it tf. The time of flight is equal to 2 times u sine theta all over g. And let's put a box around that, because that one is probably something that it will be very useful. The time of flight, the total time of flight, is equal to 2 times the initial velocity times the sine of theta over g. And this initial velocity here is interesting because that u, that initial velocity, is, well, where do we get that from? How can we tell what the initial velocity is? I mean, we could go and get a set up, you know, some sort of a video camera type thing that's watching the ball as it comes out, and we could calculate, you know, with some sort of a measurement scale. We could do the velocity, you know, crudely, is distance over time. We could do that, but we can do it another way as well, just by using a bit of maths. Well, that u there, we know that the energy at the top, the gravitational potential energy, is equal to mgh, change in h. And we also know that if there's 100% transformation, which we know that there's not, but let's assume that there is at this stage, that it's a frictionless and spherical object and there's no loss of energy in that transformation, we know that the potential energy is equal to the kinetic energy. So we know then that mgh is equal to half mv squared. And now that's cool, because in here we have velocity. So if we know the gravitational potential energy, which is just the mass of the ball, multiplied by gravity, multiplied by the height that it was dropped at, and we know the mass again over here, we can calculate the velocity that that object will actually leave and be projected from the end of that tube. So if this is a tube and the ball bearing is traveling along, and then it ejects, we can calculate the velocity at that point if we know what the gravitational potential energy is. And that's certainly not a hard thing to figure out. All right, what else might we want to know? Well, I guess let's change colors. Let's go to a black pen and look at another formula that we might want to use, because we said before we might want to know the range. And the range, if we go back up here to this bit here, the range is a distance from this here to there. That's Sx, displacement in the x direction, or what we're calling R for range. And if we make a bit of room down here, so what we're going to say is, well, we know this formula. We know from our linear motion formulas that S equals ut plus half at squared. We know that. And we know that we can go and put an x's here. We can say the displacement in the x direction is u in the x direction times t plus half of a in the x direction times t. But we also know something interesting here as well, that a in the x direction is 0. There is no acceleration in the x direction, provided it's a frictionless trajectory. So we can then go, I guess, and rearrange or rewrite that formula as x in x direction is equal to ux times t. We also know here that ux, this bit here, ux, that we can go and calculate the u in the x direction if we've got the initial velocity. And we said over here we can calculate the initial velocity, given the gravitational potential energy and kinetic energy. So if we know the initial velocity in this direction here, we know that initial velocity, then we can calculate ux, the component of u in the x direction. And it so turns out that if we do ur times cos of theta, that will be equal to the x component of the velocity. So we can now go and put this part here, we can put that and substitute it down to here. So we have Sx is equal to u cos theta multiplied by the time. But hang on, we just calculated something up here. We just said that the time is equal to 2 times u sine theta on g. So maybe we can go and put that down into here. So let's substitute in again. So let's substitute again. So we end up with Sx is equal to u cos theta multiplied by, well, let's put this in brackets for now, 2 times u sine theta over g. And we've got, if we have a look here, we've got a u and a u, so we can rearrange this formula so that Sx is equal to u squared multiplied by 2 sine theta times cos theta all over g. And now that's interesting too, because there's a mathematical rule here that says 2 sine theta times cos theta is equivalent to sine of 2 theta. So let's rearrange again. Sx equals u squared times the sine of 2 theta over g. And that, instead of calling that Sx now, the displacement in the x direction, we're going to give that a new letter now that we've talked or mentioned before, and we're going to call that r. The r for range is equal to u squared sine 2 theta over g.